All right, hello period 6, welcome to your lesson 15 video. Make sure you stick around for the entire video. There are going to be important things that I go over throughout this video that you're definitely going to need when you get started on your homework. After this video, you got to head back over to Google Classroom and you do have to submit your ASR classwork questions. The classwork questions are directly based off of everything that we're doing, in this video together. This is actually a bad lesson to not have a live session for because it is going to be more of a review session. So I'd really be, asking you guys to recall some of the things that we've done earlier in the year. But nonetheless, we got to make do with what we have. So this is a pre-recorded lesson. Anything that I go over that you have questions about, shoot me an email, come see me during office hours, or ask a question the next time we are together in class. I want to start off today's lesson just kind of going over co-functions. I know we started it the last time we met. We kind of rushed through it at the end. We were really focused on the Kahoot and reviewing for the quiz. But I just want to freshen up our memory of all the co-functions that we took a look at. So we say sine and cosine are co-functions of each other. And co-functions are equal when you have complementary angles. We talked about complementary angles being two angles that add up to 90 degrees. So the sine of an angle is equal to its co-function cosine of its complementary angle. And this definition not only goes in this direction, actually also goes in the other direction where we say, cosine theta is equal to sine and the complement 90 minus theta. So we saw that was the first one. We say sine and cosine are co-functions. The next co-function identity is our tangent theta along with our cotangent theta, cotangent of 90 minus theta. And then once again, this also goes in the other direction. We can start with cotangent, and that will be equal to tangent of the complementary angle, 90 minus theta again. And then our last set of definitions, that was our secant and our cosecant. And then once again, you could do a little switcheroo here and have our cosecant theta is equal to secant 90 minus theta. So I don't really want us to stress over these formulas. We're going to take a look at them a little bit here. We'll see them a little bit later on when we work with trig identities. But for the most part, you're not going to see this anytime soon on a quiz, okay? You'll see it in the future, but I do want to expose it to us now that we kind of finish up with our unit circle. It's also super important to note that cofunctions is a different thing than reciprocal functions, right? So a reciprocal function would be, the reciprocal of sine is cosecant and the reciprocal of cosine is secant, whereas sine and cosine here are co-functions. And then it's also important to point out that this 90 degrees at any time can be replaced by pi over 2. So we worked not only in degrees, but we also worked in radians. We spent a little bit of time together finding complementary angles, and then I think we finished last class kind of off with finding an equivalent expression, and I think we only did one example. Find an equivalent expression. So I'm not asking us to solve. I'm not asking us to evaluate. I'm just asking us to use a cofunction identity here. So find an equivalent expression, and I'm going to also put here using a cofunction identity or formula. Using a cofunction formula. We'll put formula. I should have written this on 2 lines. Let's see. Can I move this? Yes, I can. Let's copy and let's move that way over here. Okay, so find an equivalent expression using a cofunction formula. So let's take a look at the first one, and we're going to take a look at, let's maybe go back to the black one. Cosecant of 30 degrees. Right, so we're looking at cosecant of 30 degrees, and we know using our cofunction formulas that cosecant, the cofunction of cosecant, is secant. So we know cosecant theta is equal to secant of its complementary angle. So we're going to take out theta and we're going to replace it with the angle that we started the problem off with, and that's 30 degrees. And now we're going to do secant of 90 minus 30 degrees, and let's find an equivalent expression here, and the equivalent expression is going to end up being secant of 60 degrees. And that's going to be our answer here, cosecant of 30 degrees is equal to its cofunction of the complementary angle. So we say 30 and 60 degrees are complementary. Now, if you don't believe Miss Marflack, you could take a look at that 30, 60, 90 triangle that we've worked with, right? You could take a look at that. And you can see, using, I held that down for too long, using our definitions at cosecant of 30 degrees, well, cosecant of 30 degrees, that's going to be hypotenuse over opposite. Let's see, that's going to be 2 over 1, which is 2, and then secant of 60 degrees. That's going to be hypotenuse over adjacent, and that's going to be 2 over 1 as well. So, you don't have to check your work this way. I don't expect you to check your work. I just expect you to use the cofunction identity, but I'm just kind of pointing out that it works, right? It works. So an equivalent expression to cosecant of 30 degrees is secant 60. All right, and then let's take a look at just one more. Like I said, you're not going to be directly tested on this anytime soon, but it is good to kind of put it in here and expose you to it, first, and then you'll see it a little bit later as well. All right, here we are. Here's the last one. We'll do tangent of pi over 3, and I think we did one together the last class. All right, so I had a great question in my period 4, and my period 4 asked, can we convert this 2 degrees? And I said, absolutely, go for it. But I am going to show us how to solve this problem in radians. So we know tangent of theta is equal to its cofunction, and then you can kind of peek back if you want. There is the one, this is the one that we're using here. All right, that's the one we're using. Tangent theta is equal to cotangent 90 minus theta. But we have a tiny problem here. We're not working in degrees. We are working in radians. So we're going to take out that 90. We're actually going to replace it with pi over 2. All right, because 90 degrees is the same as pi over 2. And then now we can take out that theta and we can replace it with pi over 3, right? And we're going to do cotangent of pi over 2 minus pi over 3. Now you may have to take this angle work kind of off to the side somewhere. Maybe I'll put it just like right over here, some scrap work, which I'll erase after. We're trying to do pi over 2 minus pi over 3, right? We need a common denominator. So take a second, think about what would give us a common denominator. I'm seeing 6. So I'm going to multiply this by 3 over 3, and I'm going to multiply this by 2 over 2. This is going to give me now 3 pi, just multiplying the numerator straight across, and 6 in the denominator. And this is going to give me 2 pi multiplying straight across and 6, and that's going to leave me with pi over 6. So lastly, pi over 2 minus pi over 3, that is pi over 6. Now we can kind of return back to this problem here. So tangent of pi over 3 ends up being equal to cotangent, and we just subtracted these two off to the side, pi over 6. So our final answer here is cotangent pi over 6. And then once again, if you don't believe me, go ahead, let's take a quick look and a quick check, right? So tangent of pi over 3 is 60 degrees. So let's do tangent of 60 degrees over here. And tangent is opposite over adjacent. So opposite over adjacent is root 3. And then let's check cotangent of pi over 6. That'd be cotangent of 30 degrees. And that's going to be adjacent over opposite. And that is also root 3, which works out perfect and beautiful. Works out great. All right. So that is it for cofunctions. Take a second, pause the video if you don't have all of this down, but I really don't want to dwell too much on this cofunction business. We're going to see it again when we work with trig identities, okay? We're going to see it again when we work with trig identities. And now I want to get into our lesson because this was kind of like a continuation from the last lesson, erasing here. I want to get into our next lesson, and our next lesson is really a cumulative review. So every now and then, I like to take a nice pause in the course and just evaluate and kind of think about all the places we've been and everything that we've done. And this is a great time to kind of pause and do a cumulative review, because we finished up the unit circle, we finished up exact values, and we're kind of embarking on, we're getting closer to marking period 2, so we're kind of going to get started on working with these more complex formulas. And working with these more complex formulas, it'll be good to have, just this overview of everything we've done since September, and the goal is, as we're working, more and more, you're getting better and better at maybe these things that we learned early on in September. And then the sad part is that this kind of would have been a great lesson to have live together, because I would love for people to remind me of definitions, for people, it'd be a great lesson to do some volunteering, refreshing the memory, but we're just going to take you through a very quick overview of some of the things that we've done. So this is the point where I would ask, does anybody remember what we started off the year doing? And the first thing that we started off with is actually converting between degrees and radians. That's what we started off with first. We talked about what a radian is. We talked about how radian is just a way to measure an angle, just like degrees is a way to measure an angle, and how 1 radian is when the arc length is equal to the radius. So converting between degrees and radians. And you may be thinking to yourself, Miss Marf, I already learned how to do this. Why do I have to write this down, right? The goal here is mastery, and we're going to, it really is a review. So I know you've seen it already, but the goal is to kind of now reflect on it and master it and just continue getting better and better at it throughout the year. We're going to take a look at the first one, and we're going to convert between degrees and radians. And the first one we're going to convert is 3 pi over 8. Now, this is the point where I'd ask the class, okay, does anybody remember our conversion factor going degrees to radians and then going radians to degrees? This is something you may see on an ASR question. This is something you may see on your homework. When we're going degrees to radians, we're multiplying by pi over 180. And when we're going from radians to degrees, we're multiplying by 180 over pi. All right, if you didn't get that down, I will, zoom out at the end. You can take a look at it too. All right, let's go back here to 3 pi over 8. I'm going from radians to degrees, so I'm going to have to multiply by 180 over pi. And then we tried to stay away from using that calculator. We did pi over pi. We can get rid of that. And then from here, you should be seeing that 180 and 8 are both even. So let's divide by, let's start off with 2. And then I'm seeing 90 and 4 are even. So let's divide by another 2, and we're going to get 45 here. And then these are the important skills I want to review. I want to review, crossing out across, taking out factors. And then now what we're doing is multiplying straight across. So 3 times our 45, and we're dividing it by 2. Let's do that without a calculator here, okay? 45 times 3, put the double digit number on top, so you only have to do one row here. The 3 and the 5 is 15, the 4 and the 3 is 12, and then you go ahead and you add the 1 on top. So this is going to give us 135 up in the numerator, and then we're going to have 2 in the denominator. Another important skill we have to review is long division, right? Long division. So 2 does not go into 1, but it goes into 13 6 times. And then 6 times 2 is 12. 13 minus 12 is 1, and then we bring down the 5. And then now we see how many times does 2 go into 15. It goes in 7 times. 7 times 2 is 14, and then we're left with a remainder 1. Now 2 doesn't go into 1, so at this point we put a decimal, and we bring down a 0, and 2 goes into 10 5 times. And then 2 times 5 is 10, then we're left with 0. And our final answer here is going to be 67.5. And then Miss Marflex is going to zoom out so you can see the whole picture. There it is, 3 pi over 8 is equal to 67.5 degrees. So look here, we refreshed our memory on how to convert. We refreshed our memory on some multiplying and some long division. The next one we're going to take a look at is still converting between degrees and radians, and we're going to take a look at number 2 here, and we're going to start off now with 235 degrees. You may be thinking, what's that conversion factor? Degrees to radians here, right? Degrees to radians. Maybe I should have used a highlighter instead. Degrees to radians, I'm looking at this one, and I got to multiply by pi over 180, so let's multiply by that pi over 180. And then maybe you're looking at 235 and 180, and we have to ask ourselves, what do they have in common? First, remember that this 235 is like over 1. So I'm looking at across, I'm saying, 235 and 180. At this point, I would kind of ask somebody, what they think they have in common. Hopefully somebody would say 5. So I'm going to divide both of these by 5. So let's do 235 first divided by 5. Let's do that one first. 235, scrap work off to the side, divided by 5. Doesn't go into 2, but goes into 23 4 times. 4 times 5 is 20, remainder 3, and then bring down the 5. And then 5 goes into 35 7 times with no remainder. So when I do 235 divided by 5, I am left with 47. And then now let's do 180 divided by 5, right? 180 divided by 5. 180 goes in, 180 goes in. 5 goes into 18 3 times. 3 times 5 is 15, remainder 3, bring down the 0, and then 5 goes into 36 times. So when we divide 180, we get 36. And then now I can multiply share across, and that's going to be 47 pi over 36. And you could take a second, maybe you can think about, is there any number that goes both into 47 and goes into 36? Take a second, and Ms. Marflax is going to tell you, no, unfortunately, there is a number that goes into both. All right, so that was a quick review on how to convert between degrees and radians. The next thing we talked about after we did converting between degrees and radians that was super important was writing in standard position. At this point, I would ask, does anybody remember the 2 kind of key points of writing an angle in standard position? And the first key point was vertex at the origin. And that origin is 0, 0. And then the second key point is initial side. That's the side that doesn't move. Initial side along positive x-axis. Positive x-axis. And we're going to jump in here, and we found drawing angles in standard position to be really difficult when we worked with a radian one. So we're actually going to start off here. Let's start with a degree one. Let's do negative 415 degrees. All right, so we're drawing our coordinate plane, right? Drawing our coordinate plane. Our vertex is at the origin, and our initial side is along the positive x-axis, okay? So that's our standard position to get us started. Now, it is a negative angle, and we talked about how when we work with negative angles, they open down to quadrant 4. So I'm going to pass negative 90, negative 180, negative 270, and negative 360, okay? This is negative 360 here. Now, if I added another 90, this would be negative 450. So negative 415 is somewhere between these two. So it's kind of hanging out here, this terminal leg in quadrant 4. And there is our first angle in standard position. Taking a look at the second one, usually you guys were really good with the degrees. It's the radian ones that I think were a little tricky. Number 4 here, we're going to take a look at 19 pi over 6. Ooh, 19 pi over 6. This might be a little bit more difficult. Don't you worry though, Ms. Marflax got you. All right, remember, hopefully I'm freshening up the brain when I say that we first called this like pi over 2, we called this pi, we called this 3 pi over 2, we called this 2 pi. We spent a lot of time in class actually converting these axes to denominator, whatever we're given. So we're given denominator 6, so this is like 3 pi over 6, this is like 6 pi over 6, this is like 9 pi over 6, and this is like 12 pi over 6. So I can first start off with my vertex at the origin, initial side along the positive x-axis, open upwards past 3, past 6, past 9, and past 12. Now 19, I gotta go, if I add another 3 to 12, I'm at 15. If I add another 3, I'm at 18. So this is also 18 pi over 6, right? This is all the odd sides. So this is 1 pi, this is 3 pi, this is 5 pi, and it just keeps going, So once again, we're at, 6 pi over 6. Maybe I should erase this and actually count it from the start for you guys. That might be nice to see. Yeah, I think that'd be nice. So here we're at 6 pi over 6, 12 pi over 6, held it down too long, 6 pi over 6, 12 pi over 6, 18 pi over 6, and then 19 would be just like one more after. So this one would be hanging out in quadrant 3. So that was a quick review on how to draw our angles in standard position, really bringing your attention, like I said, to these two definitions that you may see in your ASR questions. And you may also see something about standard position in your ASR questions. This would be a great time to pause the video before we move on to the next problem. All right, I'd say I'm doing pretty good here on time. After we talked about standard position, we spent some time talking about quadrantal angles. We're not going to review that. All right, sorry for the cut in the video. I did hit the lock button on my iPad, as I was kind of moving it here after we erased. What we were just finishing up saying was we were drawing angles in standard position. I said the next thing we did was quadrantal angles, and that we weren't going to spend time on quadrantal angles because we saw so much of it, this week and the week before. The next thing we're going to talk about is coterminal angles, and our directions here are going to be find two negative coterminal angles. So you should be feeling really good with coterminal angles by now. Like we spent a while on them. You should know that a coterminal angle is an angle with the same initial and terminal side, right? They share actually both sides. They share same initial and terminal side. Missing an eye here. There. And you can find this by adding or subtracting 2 pi, which we did a lot in our last lesson, and then adding or subtracting 360 degrees. So we're going to take a look at this first one here. We're going to have 585 degrees. So I want to find a coterminal angle to 585 degrees. So I'm going to start with 585 degrees, and I'm going to subtract 360. This is actually no problem. You guys should be feeling pretty comfortable doing this type of subtraction, and you're going to get 225 here. Now you want to take 225, and you want to subtract another rotation, because I want to find two negative angles, right? I want to find two negative angles. This is opposite signs. Opposite signs you subtract and you take the sign of the bigger number. So it's the same as subtracting 360 minus 225 and making our answer negative. So reviewing some of those kind of rules for integers, right? I can't do 0 minus the 5, so I'm going to regroup the 6 to a 5, and then now I have 10 minus 5, and I get 5. 5 minus 2 is 3, and then I get 135. And once again, we take the sign of the bigger number, and the bigger number was 360 degrees. So I subtracted 360, I got 225. I subtracted another 360, I got negative 135. So we have one of the coterminal angles, but I want another one. So what I want to do is start with this negative 135 and subtract another rotation. Bringing your attention here, right? Opposite signs, we subtract and take the sign of the bigger number. Same sign, we add and take the sign. All right, so we're going to be like adding these two together and take that sign, which is negative. And that's negative 495. So this was really to bring your attention to, these rules for integers. Opposite signs you subtract and take the sign of the bigger number. Same sign you add, all right, we did like an addition here. Same sign you add and you take that sign. And then our final answer here would be these two coterminals. We should be feeling pretty good, though, finding the radian ones, because we did that a lot in the last lesson. All right, after coterminal angles, the next thing we talked about was reference angles. And we had a nice definition for reference angles. It had a few key things to pay attention to. The first thing is that all reference angles are positive. All reference angles are acute. And lastly, we saw all reference angles are formed with the x-axis, right? We were always asking ourselves, how far away from the, nearest x-axis? How far away from it is it from 180, from 360, nearest x-axis? This is also something you may see on an ASR question. This is a great definition. Positive, acute, formed with the x-axis. All right, let's take a look at the first one. And I almost regret numbering this number 1. I think we were going right along here. I think we were on 5. So Miss Marfleck's actually going to do a little edit here. And I think we called this number 5. I think we did 4 before that. So this should be actually number 5. And what I'm doing right now should be number 6. All right, reference angles. Here we are. Let's get started with negative 160 degrees. All right, so with reference angles, you want to know how far away they are from the nearest x-axis. So the best thing you can do is draw them in standard position. That'll really help you. Initial side along the positive x-axis. This is negative 90. This is negative 180. We open downwards, right? And you can see how far away from negative 180 we are 20 degrees away. And remember, we use that theta prime to denote the reference angle. Keeping in mind, reference angle is positive. So even if you're working in the negative direction, it doesn't matter. It's still a positive answer. All right, I think the degree ones are easier. What we really need some practice with is the radian one. I think we need some practice with this radian one, 11 pi over 7. All right, let's draw it in standard position. And just like we did with number, what was that? Number like 3 or 4, just like we did with that one, I want to relabel these axes, right? So this is like pi over 2, this is like pi, this is 3 pi over 2, this is 2 pi. If you can remember, we took the time in class to write this with denominator 7. A half of 7 is 3.5, and we had some decimals. And then this pi is like 7 pi over 7, and this one, I add the 3.5 and I add the 7. This one is like 10.5 pi over 7, and then 2 pi is like 14 over 7. So once you label these axes with these equivalent ratios, should be easy to kind of graph from here, okay, right? I can see now 11 is right after 10.5. Then once you have it graphed, you know you want to get your reference angle to the nearest x-axis. So the nearest x-axis is 14 pi over 7. So I'm at 11 pi over 7. I want to get to 14 pi over 7. My distance or my reference angle, we say, is 3 pi over 7. 3 pi over 7. And then once again, using that theta prime notation. All right, that sums it up for reference angles. After reference angles, the next thing that we kind of talked about was working with radicals. So let's take a look at that. All right, hopefully you have all of this great stuff down. We're going to erase here. And we're going to take a look at the next thing. All right, the next thing we talked about was radicals, and we're going to get started with simplifying. I got to zoom in here. So sorry. Got to zoom in here. Okay. So simplify, working with radicals. And we're going to get started here. This is number 8. We're going to have 2 radical 12. Minus 3 radical 50, minus 2 radical 2, plus 3 radical 75. The point I really want to drive home here for you to recall with radicals is that you can multiply radicals, okay? You can multiply under the radical. So root A times root B is the same as root A times B. You can divide radicals, okay, right? You can divide radicals, but you can only add radicals when they are like radicals. So I cannot do, you know, A plus B is radical AB or anything like that, or A plus B, okay? This is a no. I don't even want to write it. I'm actually going to erase it because I don't even want to write it. But I see that mistake over and over again. I see, like, you know, radical 2 plus radical 3, and people are giving me like radical 5 or radical 6 or something. No, you can't add radicals like that. If you have 2 radical 3s and you have 4 radical 3s, then you can combine those. Those are like radicals. You could say 6 radical 3. Okay, so that's just a quick refresher that you can multiply and divide radicals, but when you're adding, we use this weird notation like A radical B plus C radical B is equal to A plus C radical B. You can only add if they're like radicals. All right, coming back to number 8 over here, we're going to want to split this into a perfect square times something else. So the perfect square for our 12 is going to be 4 times 3. Perfect square for our 50, that's going to be 25 times 2. And this is where I wish we were together and I could be asking for some volunteers here. Minus 2 radical 2 plus 3, 25 times 3. And then now bringing our attention to our perfect squares for 25 and 25. Those are going to come out in front and multiply with the number in front, okay? They're going to come out and they're going to multiply with the number in front, come out, multiply with the number in front, come out, and multiply with the number in front. Square root of 4 is 2. 2 times 2 is 4. Square root of 25 is 5. 3 times 5 is 15. Can't do anything with the 2 radical 2. And then square root of 25 is 5, multiplied by the 3, and you're going to get 15. Then from here, you're looking for like radicals. So I see 4 radical 3's and 15 radical 3's. So I'm going to combine those, the 4 and the 15, and I'm going to get 19 radical 3's altogether. And then I'm seeing here, I'm seeing something else. I'm seeing negative 15 radical 2's and negative 2 radical 2's. We're going to combine those together, and that's going to be negative 17 radical 2. And then that is going to be our final answer. So there's a quick refresher on working with radicals. All right, let's move on to number 9 here. After we worked with radicals, the next thing we kind of took a look at was solving for the missing side. And the whole point of working with the radicals is so that we can work with doing some algebra with the right triangles. And that's what we kind of set the stage for here in the next lesson, solve for the missing side. And we're going to get started off here, number 9, with a 30, 60, 90 triangle. And we have our 30 degrees up here. We got our 60 down here. We got our right angle. We are looking for our x, and I should put sides here because we were missing 2 sides and 3. All right, so when we worked with our 2 special right triangles, we kind of had 2 sets of rules. We had a set of rules for our 30, 60, 90, and those rules were your hypotenuse is equal to 2 times your short leg, and then your long leg is equal to root 3 times your short leg. And then we had a set of rules for our 45, 45, 90. And that was our hypotenuse is equal to root 2 times a leg, and that's it. And then just, legs are equal. Okay, so let me rewrite this L. It's kind of ugly looking, to root 2 times a leg. Okay, there it is. So the first thing you have to identify, right, is which one's a short and which one's a long. This is actually our short leg, and this is our long leg. Keep in mind, when I look at my original triangle with the side lengths 1, root 3, and 2, root 3 is bigger than 1. So this is the long leg and this is the short leg, okay? So the short leg is always between the 90 and the 60, and the long leg is always between the 90 and the 30. So the first thing we're going to want to do is solve for that short leg. So we're going to take our hypotenuse is equal to 2 times our short leg, right? Short. So our hypotenuse is 3, and our short leg here is y. So we're going to get, that first one pretty quickly by dividing by 2, and y is equal to 3 over 2. From here now, you have the short leg and you want the long leg, and long leg is equal to root 3 times short, and our long leg here is x, and our short leg we just solved for is 3, 2. Now, even though you don't see it, class, this root 3 is over 1. So I'm going to multiply straight across here, and we're going to get 3 root 3 over 2. All right, and then that's it for solving for the missing side. All right, look alive, guys. I think we have 2 more to go through. I know I'm going pretty quick, but once again, this is a review. So everything here we've seen already. Everything we have seen already. Good time to pause and make sure you have all of this. If not, let's get it going with number 10. 2 more. Number 10. All right, after we did our 30, 60, 90 triangles, we moved on, and then that kind of set the stage for our trigonometry, right? So we got started on our trig. Why won't this erase? Oh, well. 10. We set the stage for our trig, and before we actually did any special angles on the unit circle, before we did any of those, if you can remember, we did trig of any angle, meaning we just had the angle called theta, and we were working with mostly side lengths of a triangle instead of working with the angle here. So given tangent theta is 3 over 1, and theta is in quadrant 3, solve for secant theta. And if you can remember, we actually started off not just solving for, one trig function. We actually said find the 5 remaining trig functions, or kind of find them all. So a problem like this can be hard to approach, but, the first thing you need to recognize is that we are in quadrant 3. All right, that's the first thing. It says quadrant 3, so let's draw that triangle in quadrant 3. The next thing is we're going to want to label this triangle in relation to the tangent function that's given at the beginning of the problem. Tangent is 3 over 1, so this is opposite over adjacent. So opposite is 3, adjacent is 1. And then I encouraged us to take a step back, look at our triangle, see what we got. And I have to point out here, which everybody always forgets, is that this leg is negative and that leg is negative. And it makes sense. Negative divided by negative is positive. So, you know, this theta could have been in quadrant 1 or in quadrant 3 here. And it just so happens in the directions we're given that it's in 3. All right, and then now we have to solve for that missing side, and I could not believe that my period 4, I had to wait a long time to get a response from them. They forgot how to solve for that missing side, and we finally got to it. And somebody finally said, oh, the Pythagorean theorem, we're going to solve for that missing side, right? We did a squared plus b squared equals c squared, right? You could take any legs, and we're going to solve for the hypotenuse. So negative 3 squared is 9, negative 1 squared is 1, and then we're going to get 10 is c squared, and then you're going to get root 10 is c. So this missing leg here is root 10. And then now we can solve for our secant theta, and keep in mind that secant is hypotenuse over adjacent, and our hypotenuse here is root 10, and our adjacent is negative 1. So then secant theta would just be negative root 10. And that was our final answer. All right, after we did trig functions of any angle, we took a look at the quadrants. So I do want to do one example with quadrants, and then we're done. And then we are done. So here it is. I think this is 11. What quadrant must theta lie in? And you're given this piece of information. You're given cosecant theta is less than 0 and cotangent theta is greater than 0. For this one here, we would use our all students take calculus quick refresher, right? All trig functions are positive in quadrant 1. Sine and its reciprocal cosecant is positive in quadrant 2. Tangent and its reciprocal is positive in quadrant 3, and then cosine and its reciprocal is positive in quadrant 4. So I'm really saying here, you know, where is sine theta negative and where is tangent theta positive? And then we did one at a time, right? We took this little chart. We said, oh, okay, sine theta is negative. That's going to be negative wherever it's not positive. Sine is positive in 1 and 2. Therefore, it's negative in 3 and 4. So that kind of satisfies those two very ugly check marks. Those two very ugly check marks, which I'm making kind of nicer now. Those two check marks satisfy this first condition. And then we had to go to our second condition, say, okay, where is tangent positive? Tangent's positive in 1 and 3. And then wherever you had the double check mark is where it was positive in both. And that would be quadrant 3. All right, so once again, this video I think was kind of nice because it wasn't an hour. It does kind of suck that I couldn't ask you guys questions and, you know, no participating. But this was just kind of like a quick overview of pretty much everything that we've done this year. Now, I know we've done a lot more than just what was on this, you know, like quick review. But this summed up a lot of what we did. And the goal is, you know, we're getting better and better at this. We're doing more and more. So now things that we did, you know, in September, earliest September, you know, working with the radians, you should be feeling more and more comfortable by now. When we're done, you know, here now we're done with this review. Our next lesson, we're going to be starting to work on some formulas. And that's when things I think start getting a little bit harder and harder. Now, I didn't review trig functions of special angles because we just took a quiz on that, right? So in this lesson, you didn't see anything like, you know, cosecant of negative 7 pi over 6. Like we just did that. We just did those things. You know, we did cotangent of 15 pi over 4. We did that fun stuff already. And we did it not too long ago. So that wasn't included in our review, but pretty much anything that we may have forgotten was included in this review. Make sure you head over and do your ASR questions. If you have the notes from this video, the ASR questions should be nice and easy, and then do your homework. Email me if you have any questions, and good job today, guys.